electrolysis. Please, if you have not joined the channel, this is STEM Cafeteria, makes everything science, technology, engineering, and mathematics fun, easy to comprehend, assimilate, fun, and entertaining. Kindly join, subscribe, share. Thank you very much as you do that. We have discussed about electrolysis, preference, and electrodes, and some other terminologies. Now let's talk about the quantity of products liberated as electrodes. Around 1833, we had a scientist called Faraday, and he made, investigation, research, and whatever. And generally, it was realized, probably not by only him, that the products liberated as electrodes during electrolysis is dependent on mainly three things. The first one is the magnitude of the steady current passed. The second one, the type of flow of the steady current. And the third one is the ionic charge of the liberated elements. The first two conditions, we talk about that one when we are talking about the same element over and over again. How do I mean? This one, when you are talking about the same element, if you have the same charge and some other, they have the same characteristics. So, when you are talking about the ratio or proportion of the liberated quantity as the electrodes, you can talk about the comparison of the steady current and the time of flow of the steady current. This is encapsulated in the first Faraday's law of electrolysis, and it states thus. So it says the mass M of an element discharged during electrolysis is directly proportional to the quantity of electricity Q passing through it. So let's look at this. It's saying that M is proportional to Q. I know that Q is equal to IT, that is current times time. Therefore, M is proportional to I and C. This captures the first two parameters or conditions. That is the magnitude of the steady current passed and the time of flow of the steady current. Now let's make it like this. M is equal to EIT. Here E will be called constant. As I was telling you before, I said that this one we can easily talk about it when we are talking about the same element. We have a flow current to pass through them through the same element with different quantity or different value of current and time. Now, what do I mean? Let's talk about one specific element, like element Z. E will be the same thing for Z, either in tropics or in the Sahara. E will be constant every time. Now, we are now saying that since E is constant, if current I, let's say current I to be equal to 6 ampere, and it passed through for time 20 seconds. So Q is equal to 120. Let's say that the mass discharge is equal to N. So mass Z is equal to E times 120. Now, we are now saying, let us reduce the time to 10 seconds. So, let's see what it will be. In this instance, Q is equal to 60 coulombs. So, we are going to have mv2 to be equal to this Ez. Ez will be constant also. It is the quantity of electricity that is changing times 60. And which means that mv2 is equal to mv over 2. You can see. Now, let us change the current to 3 and time to remain 20. So, if I equals 3 ampere and T equals 20, Q is equal to 60 again. So, let's see. mz3 is equal to Ez times 60. You can see. And that will give us mz3, which will still be mz over 2. So you can see, when we are talking about the same element, these constants will be the same for them. And then, with the interplay of the time and the current, that will determine the quantity discharged at the electrodes. So, for this one, we are talking about the same element in under different quantity of electricity. So that is what the first law of Faraday is talking about. So, if we bring element Y, element X, any element, this is the way we treat it for them separately. That is what Faraday this law is talking about. Please, I have my reason for stressing this because that's what confuses students most times. The first law is talking about the same element discharge under different coulombs, under different quantity of electricity. Now, assuming we now change the two, we change this one to higher, we change this one to higher. Let's say, okay, let's change this one to 12, let's change this one to 40. So, in this instance, I equals to 12 ampere, C equals to 40, Q is equal to 480. So which means that MZ4 is equal to EZ times 480, which is equal to 4 So you can see everything we are still talking about one type of element. So if it is Y, you handle it like this. If it is X, under different conditions, that is when the same element is subjected to different conditions of Coulomb, either I is changed or T is changed. So either of the two can change. Now let's go to the second law. Now, second law states when same quantity of electricity is passed through different electrolytes, the relative number of moles of elements discharged are inversely proportional to the charges on the ions of the elements. So what we are saying is this: if charge Q, you can see, please take note of this. We are talking about moles and charges on the ions. Please take note of this. This is important. That's why I said the first two is about the same. I already made that statement. This third one is what we are putting into consideration here. In this place, we are talking about moles. So what we are now saying is that if Q discharge 1 mole of univalent, ion or atom. Let me put it atom. So let's say this is A, it has plus. If it can give us 1 mole of A, it can give us 1 mole of A plus. It means that if we pass this same charge quantity through this, it's going to give us half. If we pass it through the one with 3, you understand? Trivalent. It's going to give us C over 3. This same quantity of electricity will give us moles, which is inversely related to the number of charge on it. That is what this second law is talking about. When the quantity of electricity is passed through different electrolytes, the relative number of moles of the element discharged are inversely proportional to the charges on the ions of the elements. Now let's also look at it from this way. We talk about series. When it's in series, currents will be equal. Let us now say, okay, we have this one. We talk about resistance in series. So, just to have an idea, let us say in this case, we want to discharge element A, which has A plus, element B, which has B2 plus, element C, which has 3. And this quantity of electricity, it gives us 1 mole. It gives us 1 mole of this one. Invariably, because the current and the time is the same for all of them, it's going to give us 1 over 2 moles of B. It's going to give us 1 over 3 moles of C. You can see. So that is where this one comes to play. Inversely proportional to the charges. You can see. So it has already cleared any question that we might have concerning this. Now, we note one thing. If for electrolysis, 1 mole of univalent atom will need 6.02 times 10 raised to the power 23 electrons. Because it will need 6.2 times 10 raised to the power 23 atoms. and everyone will have one electron to handle. So if it is 1 mole, Faraday discovered that the quantity of electricity needed is 96500. Now, let us now say 96500 passes through this place. It's going to give us 1 mole of A plus, half mole of B, 1/3 moles of C. You can see. So which means that for this 1 mole of this one to be generated, we need 96500 times 2. You can see. For this one, we will need 96500 times 3. So that is the major thing you need to know about the second law. And I generally talk about electrons. You know, when we are balancing electrolytic reactions, we talk about the flow of electrons. So if I'm going to talk about something like H plus now, you know, it will need E to give me H. Get that? It will need E to give me H. Now, I will need H twice to give me H2 gas. That is 1 mole of hydrogen gas. I will need 2 moles of electrons. So for a mole of hydrogen gas to be liberated, it means, that's why I talk about what's it called, electrons there. It means I need 2H plus plus 2E minus to have this balanced equation. So what does it mean? It means I will need 2 times 96500. So whenever you are talking about this Coulomb, talk about the total electrons, moles of electrons required to discharge 1 mole of the elements. Now let's look at another one. Look at this. Ca is going to give me Ca. You can see that I need 2 moles of electron to give me 1 mole of calcium. So it means that for this one, I will need 2 times 96500. That is it. One more. Let's say I want to work on this one, O2 minus. It's going to give me, let's say, O plus 2E. You can see. So you can see that I cannot have it as oxygen atom alone. It means that I will need O plus O to give me O2 gas. And how does that happen? It's going to be 2 O2 minus plus 4E to give me O2. Oh, sorry. Let me put minus here so it makes sense. 2 O2 minus 4E to give me O2 gas. If you look at this, I will need 4 moles of electron to have this, the gas. So which means that for this one, I will need 4 times 96500 coulomb. So that is how it is being done. The first one, if you are talking about the same element over and over again. But in this instance, when we are comparing elements of these different valences, that is what happens. Now, look at this one. Look at this. Let's say you have sodium plus H chlorine. For this one, I will need to give me Na. So just, if this is the only one in the reaction, I will just need 96500. Let's look at this one now. If this is H plus, let me put it this way. I'm going to have H. You know, this is not complete. I will need another H for this one to exist. For me to have 1 mole, I'm going to have 2H plus minus 2A minus to give me. This one cannot be H2 gas. This is where H2 gas can exist. So it will need 2 times 96500 quantity of electricity, coulomb. Just like when I calculated that of oxygen. Look at this one too. So no, sorry, this one should be plus Cl minus E should give me Cl. So, and this one cannot exist alone. So I can have it like this: 2Cl minus 2E minus to give me Cl gas. So you can see 2 times 96500 coulomb. What I'm trying to show you is this. If it is just ordinary sodium, you need 96500. But for this one, you will need 2 times because of the way they exist in nature. Because of the way they exist in nature. But if they exist together, where the what's it called? Electrolysis require sodium and hydrogen, sodium and chlorine to be liberated. Because this one will need two. We are going to discharge two of this. Because this one we need two. We need two of these ones to be discharged. So you will see what I write now. Now let's think about if we have sodium ion as the cathode and Cl minus as the anode. You know, this one just needs to give me energy. That's all. But this one will need to give me Cl gas. And for the equation to be balanced, this one and this one must, if this one takes this electron, this one should liberate this one that this one will need. So it means that for 1 mole of chlorine gas, we will need to discharge 2 moles of sodium molecules. So what I'm saying is this. So at this place too, we have 2Na plus 2E minus to give me 2Na. Solid or whatever. So this one now. So this is the anode. I think this is cathode. So this one will now be 2Cl minus 2E to give me Cl gas. So you can see. So this will balance the equation as we thought to. So this will balance the equation.